That we deal with these two questions. First questions let us to prove that if the stochastic process x of t is a real WSS process, and then its autocorrelation functions is real and even. Its power spectral density functions is even and non-negative. So let us begin. First, we write the definition of the autocorrelation functions of our WSS process. So we can see this is just like this, and then we know that xt is a real process, so the conjugate can be cancelled. It is just equals to x of t plus tau times x of t. In that case, of course, the autocorrelation functions is real. Then we can also change tau to minus tau, and what we get is just x of tau times x conjugate of t plus tau, and what we get is just that it also equals to r of rxx of tau conjugate, because rx autocorrelation functions of this process is real, so they are just the same. Because of this is even functions. And for the power spectrum of the process, first we write the definition. It is a Fourier transform of the autocorrelation functions. Then we depart from minus infinity to infinity to 0 to infinity and minus infinity to 0, and change it upside down, and and then change tau to minus tau, and what we get is change the integrate region and change the d tau to d minus tau. We get 2 minus sign, so it cancels together. And finally what we get is just look like this. Then we change the omega to minus omega. What we can get is just itself, so it is even functions. And then we need to prove that this functions is a non-negative functions. In this case, we dispense the e to minus j omega tau to cosine omega tau minus j sine omega tau. We can see at this part, our autocorrelation functions of the process is even functions, and the sine omega tau is odd functions. The integration of this two is just equals to 0. So we just need to concentrate on the first part. As the first part, we can dispense tau to alpha minus beta, and in that case we need to do integrate twice time, and then we dispense cosine omega alpha minus beta to cosine alpha times cosine omega beta plus sine alpha times sine omega beta. In that case, what we get is 2 times the expectation of the integrate from minus infinity to infinity, x of t times cosine omega t alpha plus 1 square, and 2 times expectation from integrate from infinity to minus infinity to infinity, xt times sine omega t dt square. And this is, of course, is bigger than 0, so it is non-negative. So, and the second question asks us for the following functions, it can represent an autocorrelation function of a WSS stochastic process, or can represent a spectral density functions. So let us see. We can see the first functions. If it is autocorrelation functions, we can see at the tau equals to 0, it is a discontinuous signals, so I think it may not be autocorrelation functions of a stochastic process. Then, if it is spectral density functions of autocorrelation of a WSS process, we need to do the inverse Fourier transforms to get the autocorrelation functions of the origin process and see if it is right. Then we get the inverse transforms, and what we get is just like this. It is pi over 1 times 1 over pi times 1 over tau square plus 1, and it is, of course, is non-negative, so I think it can represent power spectral density functions. Then the second function is easy to look. We can say it's just a square of sinc functions. We can regard it as sinc functions times itself. If it is autocorrelation functions, of course we can see. Wait, let me think about it. Sorry. Okay. It is sinc functions. Yes, it is just a sinc functions times itself. So it is of course non-negative, and it is of course continuous. Yes, it is of course continuous, and it is get its maximum at the v equals to 0. In that case, I think the B is of course can represent autocorrelation functions of WSS stochastic process. Then, if it can if it represents spectral density functions of a process, we can see the spectral density functions is just autocorrelation functions get a Fourier transform. So in a Fourier transform, two sinc functions times together is equals to the inverse Fourier transform of the sinc functions convolution with itself. So what we get is just two square wave convert with themselves. What we get is just like a triangle, and of course this triangle is non-negative. So I think, and there can be autocorrelation functions. So we think F is also can represent power spectral density functions of a stochastic process. And then for the third questions, first we can see that the signal is discontinuous, so it can't represent autocorrelation functions of a WSS stochastic process. Then if it represents power spectral density functions, its inverse Fourier transform is a sinc functions, and the sinc functions isn't a non-negative functions, so it is also can't represent power spectral density functions of a WSS stochastic process. Thank you very much.